So now that we have this chart, know for a fact that PE will still be the majority of the energy because only 1/3 of the time has passed. So we can say it's approximately the PE at t equals 3, or t equals t over 3. We know that the kinetic energy is going to be a smaller amount, as there's still more time to go, or time to accelerate. We also know that the KE added with the PE at t over 3 will not add up to the ME at t is equal to 0 because of frictional forces. We can say that the work due to friction would cover the rest of the gap. So there is some energy lost here. So these, the KE and the PE will not add up to the ME, so energy is not conserved. We're now on I2, and this is asking for a momentum versus time graph. And we know that momentum, or P, is equal to mv. So when graphing, we know that doing a momentum over time is going to look the same as doing a V over T graph. So we can draw this starting from rest. We know that the object starts from rest and then begins to accelerate at a constant rate. So this would just be increasing over time by the same rate. So it will be a linear function. Now, the third and final part, asks how would the momentum versus time graph from the previous part change if the coefficient of kinetic friction were to be increased. So it's asking if UK were to be increased, how would this graph change? That question is very simple, as we know that the slope of a momentum over a time graph is almost A. So it would be mv over t is what this slope is. The slope is mv over t. If we divide this by m, so if you divide the slope by m, then we would just have a v over t, which would also be a. So the slope divided by the mass is equal to our acceleration. So we know that if our mu k were to increase, then our force of friction would increase as well, because we know that force of kinetic friction is equal to the Fn multiplied by the mu k. So the bigger the mu k, as long as Fn stays the same, which it is in this scenario, we know that the force of kinetic friction will also increase in turn. So as mu k increases, Fk will also increase. And we know that our equation for finding A is g sine theta minus cosine theta multiplied by the mu k would equal our A. So the bigger this subtractive force is, the smaller our A will be. So in turn, as mu k increases once again, so as our force of kinetic friction increases, we know that our A will decrease in turn. And so if our A decreases, as the slope of the graph is related to A, although it does not exactly give us A, we know it's related, then in turn our velocity is going to go down over the same rate. As our t stays the same, our velocity will decrease as our acceleration has stayed the same. So our slope would decrease in turn. So it would be a smaller slope. It would not increase by the same amount any longer. It would look something like this. And that is all for this FRQ.